Welcome back to The Anesthetist. I always like to ask, where are you listening from today? Is it morning, evening, or maybe late at night? When the world is quiet. Wherever you are, you're part of this journey with me. And today we're exploring wormholes again, but from a different aspect, not just shortcuts through space, but something deeper. If you enjoy wandering through these ideas together, don't forget to subscribe. It means you'll be here for the next step we take into the universe. Chapter 1. Goodbye, long trips, and how wormholes could make space small. Imagine planning a trip to the nearest star outside our solar system, Proxima Centauri. With today's fastest spacecraft, that journey would take more than 70,000 years. That's longer than all of recorded human history. Longer than the time since humans first painted on cave walls. It's so long that it feels impossible. Like a goal we could never realistically reach. We can send probes, but for humans, such a trip would span hundreds of generations. Now picture stepping through a doorway and arriving there instantly. No months in space, no decades, no need to survive in a ship for a lifetime. Just one step, and you're standing under the light of another star. That's the idea behind a wormhole. Not as a fantasy, but as a possibility allowed by the laws of physics. A wormhole is a tunnel in the very structure of reality, what scientists call space-time. We usually think of space and time as separate things, but in physics they're woven together, forming a flexible fabric. You can think of it like a sheet of paper. If you draw two dots on opposite sides, the normal way to get from one to the other is to travel across the flat sheet, following the surface. But if you fold the sheet so the dots touch, the journey becomes instant. A wormhole is that fold, but instead of paper, it's the geometry of the universe itself, bending in a way that allows two distant points to connect directly. What makes this so powerful is that it changes the rules about distance. With current technology, the only way to go from one place to another is to cross the space between. We are bound by speed and even light. The fastest thing in the universe needs over 4 years to travel from Proxima Centauri to Earth. But a wormhole skips the in-between. If one end is here and the other end is there, travel time is simply the time it takes to step through. You wouldn't be breaking the speed of light because you're not moving through normal space. You're taking a shortcut through space-time itself. If we could create a wormhole from Earth to Mars, the trip would take seconds instead of months. A wormhole to a planet in another star system would take seconds instead of centuries. Entire parts of the universe that are now unreachable could suddenly be within human reach. We could explore not just our solar system, but dozens, maybe hundreds of others in a single lifetime. The map of the universe would shrink, not because the distances changed, but because the paths between them did. And wormholes wouldn't just be for travel. They could change how we communicate long before they change how we move. Today, when NASA sends a signal to a spacecraft like Voyager 1, which is far beyond the edge of the solar system, the message takes almost a full day to arrive. If astronauts were on Mars right now, conversations with Earth would have a delay of several minutes each way. Through a wormhole, the delay would disappear. We could talk to distant crews in real time. A colony orbiting another star could send and receive information instantly, as if it were right next door. This might be the first real use of wormholes, if we could make them, linking far-off places for instant data transfer, long before we send humans. The physics that allows wormholes comes from Einstein's theory of general relativity, the same theory that explains black holes. Einstein's equations describe how mass and energy curve spacetime, and how objects move along that curved shape. In the mid-21st century, physicists noticed that certain solutions to those equations looked like tunnels connecting two regions. These were purely mathematical at first, and the earliest versions weren't stable. They would collapse before anything could pass through. But they showed something important. The universe doesn't forbid such connections. It only makes them very difficult. The main problem is stability. Space-time, left to itself, would try to close the tunnel instantly. To hold it open, you'd need a kind of matter with negative energy density, exotic matter. This isn't the same as dark matter or antimatter. It's stranger still. We've seen hints of it on very small scales in experiments like the Casimir effect. But making enough of it to stabilize a tunnel would be one of the hardest engineering challenges imaginable. Still, in principle, if you could surround the throat of a wormhole with enough exotic matter, it could stay open long enough for a person or even a ship to pass through. If that happens, the consequences go far beyond transportation. Think about how every major leap in travel technology has reshaped civilization. Ships connected continents, railways connected cities, air travel connected countries across oceans. Each time the world became more integrated, economies grew and cultures mixed. But each of those still had limits. Oceans, fuel, time. Wormholes would erase those limits entirely. The word remote would lose its meaning. A mining base on a distant moon could send resources back to Earth instantly. A disaster on another planet could be met with emergency crews within minutes. Scientists could study alien ecosystems in person and return the same day. Of course, the benefits would be balanced by risks. With no travel time, there would also be no natural barrier against the spread of harmful organisms or even political conflict. A wormhole could move people, but it could just as easily move weapons or invasive species. The same doorway that brings help could bring harm. That's why, even if wormholes became possible, their use would almost certainly be heavily controlled. Whoever managed them would hold incredible power, the power to decide who or what gets to cross between worlds. And there's another challenge: trust. Space travel today takes time, and in that time there are chances to prepare, to monitor, to respond. With a wormhole, events could happen faster than warnings could be sent by normal means. That could make both diplomacy and defense much more complicated. But even with the risks, the possibility of making the universe smaller is one of the most exciting ideas in science. It's not just about getting somewhere faster. It's about changing our relationship to the universe itself. We've spent all of human history looking at the stars as something unreachable, as destinations for the distant future. Wormholes would take those futures and bring them into the present. Right now, they remain an idea on paper and in equations. But so did many other technologies that define our lives today. 100 years ago, the idea of people walking on the moon was a dream. The idea of handheld devices connecting you instantly to someone on the other side of the planet was fiction. Science has a way of turning today's impossibilities into tomorrow's normal. If wormholes ever become real, it won't just be a change in technology, it will be a change in perspective. The universe will no longer be a vast, unreachable expanse. It will be a network, one we can step into, explore, and connect in ways we've never imagined. The first time someone steps through and returns with proof, that moment will mark a new era in human history. And maybe, when that day comes, we'll look back on our long, slow journeys through space, the way we look back on the days before airplanes or the internet, as a time when the world felt much bigger than it really was. Chapter 2: Bending Space. The basic science behind wormholes. If you've ever seen a photo of Earth taken from space, you know how small and round it looks. Everything we know, every person who's ever lived, exists on that thin blue surface. We're used to thinking of space as the huge, empty black around it, something far away, separate, out there. But physics tells us space isn't just empty, it's something real. It has shape, it can be bent, and it can be stretched. The idea of a wormhole starts with that bending. Over a century ago, Albert Einstein changed the way we think about gravity. Before him, gravity was imagined as an invisible force pulling objects toward each other. Newton's laws worked well for most situations, but they didn't explain everything. Einstein looked deeper and proposed something more surprising: that gravity isn't really a force at all. It's the result of mass and energy curving space-time, the four-dimensional fabric that combines space and time into a single thing. It's not easy to picture four dimensions, but we can use a simple analogy. Imagine space-time as a giant trampoline. Place a heavy ball in the middle, and the trampoline sags. If you roll a smaller ball nearby, it curves toward the heavier ball, not because the heavy ball is pulling on it directly, but because the surface it's rolling on is bent. That's how planets orbit stars. They're following curves in space-time created by the star's mass. Once you accept that space can bend, you can start asking new questions. If mass can bend space into a curve, could something bend it enough to fold it over completely? Could two distant points be brought right next to each other in the fabric of the universe? In the 1930s, Einstein and a colleague named Nathan Rosen found that the equations of general relativity allowed something like this: a mathematical bridge between two regions of space. The bridge wasn't stable, but it was there in the math, and that was enough to get people thinking. The concept that followed became known as a wormhole. In simple terms, it's a connection between two places in space-time. You could enter one side and emerge from the other without crossing the space between. The distance outside the tunnel might be light years, but the distance inside could be just a few meters. That sounds like breaking the rules, but it's not. The laws of physics have a strict limit. Nothing can move faster than light through normal space. A wormhole doesn't break that limit, because you're not traveling through normal space. You're taking a path that's shorter in space-time itself. Think of two cities connected by a mountain road. You can drive over the mountain, or you can take a tunnel through it. The tunnel doesn't make you faster. It just gives you less road to cover. Of course, this is still theory. We've never seen a natural wormhole. We don't know if they exist anywhere in the universe, but they're not forbidden by the equations that describe how space-time works. And that's what makes them exciting to scientists. If the math says something is possible, the next step is to ask how it could happen in reality. One possibility is that wormholes could form naturally in extreme environments, like near black holes or in the violent conditions of the early universe. Another is that they could be created artificially by a civilization advanced enough to manipulate space-time directly. In either case, the real challenge is keeping them open. The natural tendency of space-time is to close the tunnel instantly, cutting off any passage. That's where exotic matter comes in, a strange form of matter with negative energy density that could hold the tunnel apart instead of letting it collapse. We'll get into exotic matter later, but for now, the important point is this: wormholes are not just science fiction. They are a real solution to real equations. They don't break physics. They work within it, at least on paper. And that means, in principle, they could exist. The universe already surprises us with phenomena that sound impossible until we see them. Black holes were once only theoretical. Gravitational waves, ripples in space-time itself, were just predictions until detectors recorded them in 2015. Wormholes might be the next surprise waiting for us. And if they are, they'll change not just how far we can go, but how we understand distance, time, and the shape of reality itself. Chapter 3. The strange material that could hold a wormhole open. If you imagine a wormhole as a tunnel through space, it's tempting to think of it as solid and dependable, something you could reinforce the way you would shore up a mine shaft or build a bridge. But space-time doesn't work that way. It's flexible. It responds to mass and energy, and the same flexibility that lets a wormhole exist also works against it. Left alone, the tunnel would pinch shut almost instantly, sealing both ends before anything could pass through. This isn't just bad luck. It's built into the laws of physics. The shape of a wormhole wants to collapse because of gravity. Every bit of mass around it pulls inward. Even light, which normally moves freely through space, would curve and fall toward the walls of the tunnel. The structure wouldn't just be unstable. It would be catastrophically unstable. You could never send anything through before it was gone. That's why scientists realized that if you ever wanted a wormhole you could actually use, you'd need something to push back against that collapse. And not just any push would do. Ordinary matter, atoms, molecules, planets, stars, always pulls inward under gravity. What you would need is the opposite, matter that doesn't pull at all, but repels. This is where the idea of exotic matter comes in. Exotic matter is a catch-all term for material with negative energy density. It's not antimatter, which is still normal, in the sense that it has positive mass and falls into gravity wells like everything else. Exotic matter would be fundamentally different. If you placed it near a planet or star, instead of falling toward it, it would seem to fall away. If you lined the walls of a wormhole with it, the inward pull of gravity would be cancelled, or even reversed, holding the tunnel open instead of letting it collapse. It's a strange idea, but there is at least one place in nature where we've seen hints that negative energy is possible, the Casimir effect. This is a real, measured phenomenon in quantum physics. If you put two perfectly flat metal plates very close together in a vacuum, quantum fluctuations, tiny borrowed bits of energy that pop in and out of existence everywhere in space, behave differently between the plates than outside them. Between the plates, certain wavelengths can't exist, so there are fewer fluctuations. This difference creates a measurable pressure, pushing the plates together. In quantum field theory, you can describe this region between the plates as having negative energy compared to the outside. It's not much. The forces involved are incredibly small, but it matters. It's proof that negative energy density is possible in our universe. And if something is possible, even in a tiny way, physics doesn't forbid it from happening on a bigger scale. The problem is, we have no idea how to scale it up from a laboratory effect, measured in nanometers, to something large enough to surround a tunnel that might be kilometers wide. You can think of it like electricity in the 1700s. At the time, scientists could make static sparks and tiny shocks, but they had no way of imagining the electrical grids that would power entire cities. Exotic matter today is where electricity was back then. Something we can see in a faint, fragile form, but nowhere near the level needed for real-world infrastructure. If we ever do figure out how to create and store exotic matter in useful amounts, the next challenge will be control. Negative energy would be an incredibly powerful tool for shaping space-time. Used carefully, it could hold wormholes open, perhaps even shape them so they could connect specific locations. Used recklessly, it could destabilize existing wormholes or disrupt gravitational systems entirely. Whoever controls exotic matter would, in a very real sense, control the ability to rewrite the map of the universe. There are also safety questions. In quantum physics, negative energy is linked to unusual effects, like reversing the flow of time for certain processes or changing the vacuum state of space itself. We don't yet understand the limits of these effects, so there's no telling what could happen if large amounts of exotic matter were produced or released. Some physicists speculate about vacuum decay, a chain reaction in which the energy structure of the universe could shift to a lower state, erasing everything we know. It's an extreme scenario, but the fact that it can be discussed seriously shows how cautious we'd need to be. Even so, the pursuit of exotic matter isn't just about wormholes. It could have other uses. It might be used to counteract gravity in space travel, allowing for propulsion without fuel. It could, in theory, enable new kinds of shields against radiation, or even be part of technology that manipulates time dilation for long-duration missions. The point is, exotic matter is a gateway to more than one kind of breakthrough. Wormholes are just the most dramatic example. Right now, exotic matter is the biggest roadblock between wormholes as mathematical curiosities and wormholes as actual structures we could travel through. Without it, any tunnel we try to make collapses instantly. With it, the door to the stars stays open. The question is whether we'll ever learn to make enough of it, safely enough to take that step. It's a reminder that sometimes the hardest part of a technology isn't the big visible thing, the tunnel, the spaceship, the bridge. but the invisible detail that makes it possible. For wormholes, that invisible detail is a form of matter we've never touched, never seen in large amounts, and can only imagine for now. But the fact that physics doesn't forbid, it keeps the possibility alive, and in science, that's all you need to keep pushing forward. Chapter 4. Shaping Space. How to keep a tunnel stable. If exotic matter is the key ingredient for a wormhole, then shaping space-time is the craft of actually making it work. Having the material is one thing. Knowing how to arrange it so a tunnel forms, stays open, and is safe to travel through is another challenge entirely. The universe doesn't naturally give us perfect, stable wormholes. At least, none we've ever seen. The kinds predicted by early solutions to Einstein's equations tend to collapse too fast, or lead to places no one would want to visit, like the interior of a black hole. That means a usable wormhole would need to be engineered, not just discovered. It's not about stumbling across a cosmic tunnel. It's about building one. The shaping process would start with geometry. In general relativity, space and time aren't fixed. They bend in response to mass, energy, and momentum. To make a wormhole, you'd need to manipulate that bending on purpose. Imagine space-time as a three-dimensional fabric stretched across a frame. Most of the time it's almost flat, with gentle curves around stars and planets. A wormhole would require folding that fabric until 2 points touched, and then creating a smooth, stable connection between them. This is where exotic matter comes in. It would line the throat of the wormhole, pushing space-time outward to resist collapse. But placement is crucial. Too much in one spot, and you could distort the tunnel unevenly, creating dangerous gravitational gradients that could tear apart anything inside. Too little, and the tunnel would pinch shut. The distribution would have to be exact, maintained at all times by systems that can react instantly to any shift in pressure or energy flow. Even if the shape is right, the wormhole's entrances, the mouths, would need to be controlled. In theory, they could be anywhere, but their location would matter for safety and stability. Placing a mouth near a massive object like a planet could expose it to gravitational tides that distort the tunnel. Put it in deep space and you reduce interference, but you also have to think about how people or spacecraft get there. A practical network might place wormhole mouths in stable orbital points, like the Lagrange points between Earth and the Moon, where gravitational forces balance out. The orientation of the tunnel would also need constant monitoring. Space isn't empty. It's full of radiation, magnetic fields, and moving masses. Even small changes could ripple through the structure of a wormhole, much like wind buffeting a bridge. In an engineered wormhole, there would likely be containment rings or structural frames around each mouth, housing the systems that monitor curvature, energy balance, and environmental interference. Travel through the tunnel itself adds another layer of complexity. In the simplest models, moving through a wormhole feels instantaneous. You step in, and you're out the other side. But the interior geometry still needs to be navigable. If the tunnel's space-time curvature is too extreme, it could create tidal forces, stretching and squeezing anything inside. The goal would be to shape the throat so it's smooth, without sudden changes in curvature, so that a spacecraft could pass through without damage. There's also the question of size. A microscopic wormhole might be easier to stabilize, but useless for anything bigger than particles. Scaling up means more exotic matter, more energy, and more control systems. It's one thing to keep a tunnel a few millimeters wide open. It's another to keep one large enough for a ship from collapsing under its own geometry. And then there's mobility. Once you've built a wormhole, can you move its mouth? In principle, you could. But doing so would mean dragging a patch of distorted space-time through the universe, a process that could require enormous amounts of energy and create unpredictable effects on anything nearby. It might be easier to leave the mouths fixed and move ships to them the old-fashioned way. What's clear is that a wormhole wouldn't be a set-it-and-forget-it structure. It would need to be managed constantly. Sensors would track gravitational changes, Energy inputs would adjust the exotic matter's effect. Automated systems, likely controlled by AI, would react faster than any human could to correct instabilities before they grew into collapse. In a way, shaping and maintaining a wormhole might be less like building a bridge and more like piloting a ship. It's something that's never truly done. It's always in motion, always needing adjustment, always responding to its environment. And unlike a ship, a wormhole connects two places that could be under completely different conditions. One mouth orbiting in quiet space, the other near a bustling planet, each pulling on the tunnel in its own way. The good news is that the mathematics of general relativity already give us models for stable geometries. Physicists like Kip Thorne and Michael Morris have worked out what shapes the curvature needs to take for a wormhole to be traversable without crushing its contents. These models give a blueprint, not for a specific machine, but for the space-time shape we'd have to create. The challenge is turning that blueprint into a reality we can control. If we ever master it, the result would be more than just a tunnel. It would be a piece of engineered space-time, a human-made feature in the structure of the universe itself. And once we could shape one, there's no reason we couldn't shape more, linking not just planets, but entire star systems into a network where travel time between them drops to zero. But before we get there, the hard part is still ahead, figuring out how to keep even a single tunnel stable when the universe is constantly trying to pull it apart. Exotic matter might give us the tool, but shaping space-time into something safe, predictable, and lasting, that will be the real test. Chapter 5. Building the first wormhole. What it might take. It's one thing to imagine a wormhole. It's another to ask what it would take to actually build one. Not as a thought experiment, not as a scene in a movie, but as an engineering project with deadlines, budgets, and blueprints. The idea sounds so far beyond today's technology that it's tempting to treat it as an impossible dream. But if physics doesn't forbid it, the next question is always the same. What steps would get us there? The first thing to realize is that you don't start with a massive human-sized tunnel between Earth and a distant planet. You start small, very small. In the same way that airplanes began as fragile wooden gliders before they became long-haul jetliners, a wormhole program would probably begin with tiny, laboratory-scale experiments. These wouldn't be for people, or even large objects. They would be about proving that a tunnel can exist, can be stabilized, and can be controlled for more than a fraction of a second. At this scale, the experiment might look more like a particle physics setup than a science fiction portal. It could be conducted deep underground or in orbit, away from interference. High-energy particle collisions might be used to create the initial curvature of space-time, perhaps using conditions similar to those near a black hole. Exotic matter, if we can make it in measurable amounts, would be placed along the edges of that curvature to stop it from snapping shut. The goal at this stage wouldn't be travel. It would be to keep a wormhole stable long enough to send information, maybe a stream of photons, from one side to the other. If that worked, the next phase would be scaling up. That's when the energy demands would skyrocket. Even a wormhole just a few centimeters wide could require more energy than a city uses in a year. Containment systems would have to grow too, because you're no longer holding the geometry of a tunnel the size of a particle. You're shaping space-time large enough for atoms, then molecules, then maybe small objects to pass through. And then there's the environment to think about. A wormhole mouth wouldn't just float in open air like in the movies. It would have to be housed in a controlled facility, probably surrounded by massive magnetic fields, radiation shielding, and structural supports to handle the stresses of warped space. The facility might look less like a spaceship hangar and more like a fusion reactor, a tangle of coils, superconductors, and cooling systems humming with energy. Location would matter too. Building one on the surface of Earth could expose it to vibrations, weather, and constant gravitational interference. Putting it in orbit, perhaps at a stable point between Earth and the Moon, could reduce those stresses and make it easier to monitor. The trade-off would be accessibility. Every trip would first require getting into space. Once you have a stable wormhole large enough to send physical objects, you'd face an entirely new set of challenges. How do you keep the other end anchored where you want it? Do you build both ends in the same place and then move one, slowly, to its destination? That could take decades if you're sending it to another star. Or do you try to create the two ends simultaneously at different locations, which might require energy levels beyond anything we've imagined? Navigation would have to be part of the design from the beginning. Even if the tunnel connects two fixed points, you'd need precise control over how the mouths align in space. A small shift in one could lead to dangerous misalignment inside the tunnel, potentially destroying whatever's trying to pass through. This means the mouths would likely be mounted in massive stabilizing frames, capable of making micro-adjustments constantly. And then there's the question of who or what goes first. Even with years of testing, no one would risk sending a human into a new wormhole without absolute confidence in the exit conditions. The first travelers would be machines, probes loaded with sensors, cameras, and communication gear. They'd measure everything: radiation levels, gravitational forces, time differences between the two ends. If they return intact with consistent data, only then would the idea of human travel be considered. But even at that point, the political and ethical debates would begin. Who controls the first wormhole? Who decides where the other end goes? How do you prevent its use for dangerous or harmful purposes? The technology would be too powerful to ignore, and too risky to leave unregulated. The infrastructure around it, treaties, oversight bodies, security protocols, would need to be built alongside the wormhole itself. If all of that sounds complicated, it's because it is. Building a wormhole would be the most ambitious engineering project in human history, blending physics, materials, science, energy generation, space infrastructure, and global cooperation. It would make the Apollo moon program look small by comparison. But it's worth remembering that other once impossible projects, nuclear reactors, GPS networks, the internet, began with the same combination of theory, experiment, and perseverance. For now, a real wormhole is far beyond our reach. But if we imagine a century of steady progress, better understanding of exotic matter, breakthroughs in energy storage, advances in precision engineering, then the steps to get there start to look less like magic and more like a roadmap. The first one we build may be tiny, short-lived, and hidden in a lab, but it could be the seed for a network that one day connects worlds. And when that day comes, the biggest challenge won't be the physics. It will be deciding how to use the doorway we've just made, and what kind of future we want to step into when we walk through. Chapter 6. Where would you put a wormhole? Let's imagine that the hard part is over. We've built a working wormhole. It's stable, and it's safe enough to use. The next question is deceptively simple. Where should it go? You might think the answer is obvious. Just place it wherever we want to travel. But wormholes are not like building a road or laying a cable. They're part of space-time itself. And that means placement isn't just a matter of convenience. It's about stability, safety, and purpose. The first factor is gravity. Everything with mass, planets, moons, stars, distorts space-time. A wormhole is already a delicate structure, balanced between collapse and expansion. Putting one too close to a massive body could stretch or twist it in ways we can't control. Imagine setting up a bridge in the middle of a stormy ocean. No matter how strong the supports, constant waves would strain it. For wormholes, those waves are gravitational tides, and they can be subtle or extreme depending on the location. That's why many scientists think the safest places for wormhole mouths would be in what are called gravitationally stable points, like Lagrange points. These are spots in space where the gravitational pull of two large bodies, for example, Earth and the Moon, balance out with orbital motion, so that an object placed there stays in position with little fuel or adjustment. We already park satellites at some of these points, because they offer a stable, relatively undisturbed environment. The same qualities could make them perfect for wormhole placement. Distance from Earth is another big consideration. Putting a wormhole mouth on the planet's surface sounds convenient. You could just walk up to it, but it would expose it to constant environmental noise. The Earth's rotation, tectonic shifts, atmospheric pressure changes, even daily heating and cooling could affect the fine control needed to keep it aligned. And if anything went wrong, an instability, a sudden collapse, the consequences would be felt right where people live. Space-based locations, by contrast, remove many of those risks. A mouth positioned in high orbit or at a Lagrange point could be monitored from nearby stations without endangering Earth directly. It would also make it easier to connect the wormhole to destinations in space, other stations, mining operations, or planetary colonies, without having to first launch from the ground. The trade-off is accessibility. If you want to use the wormhole, you have to reach it first, which means maintaining a steady and reliable shuttle system. Then there's the question of what's on the other side. If we're connecting Earth to another planet or star system, the far mouth would have to be placed with the same care. If it opens near a planet, it should be in orbit, not on the surface, for many of the same safety reasons. The location would need to avoid debris fields, radiation belts, and gravitational hazards. An unstable orbit could slowly drift the mouth into dangerous regions, or cause it to require constant adjustments that drain energy and resources. But practical concerns aren't the only factor. Politics would play a role from the very first decision. A wormhole is more than a piece of infrastructure. It's a strategic asset. Where you put it determines who has access, who controls it, and who benefits. A wormhole mouth in international waters or on neutral territory might seem fair, but controlling access in open space is far more complicated than controlling a harbor or airport. A mouth inside a nation's borders could quickly become a geopolitical flashpoint, especially if the other end connects to valuable resources or habitable land. Security is another layer. If a wormhole is a two-way door, then whatever is on the other side can come through just as easily as we can go there. Placement would need to account for how you defend it, inspect travelers, or even close it entirely in an emergency. For that reason, many people imagine wormholes surrounded by large, heavily monitored stations that act as customs checkpoints. These stations wouldn't just handle security, they'd also manage traffic, regulate the flow of ships or people, and keep the wormhole stable. You also have to think about scaling. The first wormhole might connect two fixed points, but once more are built, we could have a network. That network's layout would matter as much as where individual wormholes are placed. The wrong arrangement could create bottlenecks, just like bad highway planning creates traffic jams. The right arrangement could turn travel between worlds into something as easy as changing trains at a busy station. And finally, there's purpose. Not every wormhole would be for people. Some might be built purely for freight, delivering resources from one mining operation to another, or moving goods from a manufacturing hub to multiple colonies. Those could be placed in completely uninhabited areas, designed only for automated ships. Others might be for science, giving researchers instant access to extreme environments like the surface of a distant moon or the edge of a black hole's influence. In those cases, placement would be about maximizing data and minimizing risk. The decision of where to place a wormhole would set the tone for how it's used. A well-placed wormhole could become the backbone of peaceful trade and exploration. A poorly placed one could become a constant source of conflict, instability, or even danger. In many ways, this decision would be as important as building the wormhole in the first place. We might imagine the first one opening in orbit, connected to a carefully chosen point near a nearby planet, perhaps Mars. Safe distance, predictable conditions, and a manageable first step into a much bigger future. From there, the network could grow to the moon, to asteroid mining sites, to deep space research outposts. The placements would evolve as our reach expands, each new wormhole adding a link to the chain of human presence in space. And with every new link, the question of placement would repeat: where is it safest? Where is it most useful? And who will have the keys? Because once the door exists, its location will decide everything about who walks through it and why. Chapter 7. The first thing through a wormhole might not be us. When we imagine the first use of a wormhole, we tend to picture a person stepping through, an astronaut in a sleek suit, vanishing in one place and appearing instantly in another. It's an image pulled straight from science fiction, but in reality, if a wormhole were ever built and stabilized, we would almost certainly send something else first. Not people, not even animals. Most likely, it would be a stream of data. There's a good reason for that. Wormholes, even if stable, would still be untested environments. We wouldn't know how they interact with physical matter over time, or whether subtle effects could accumulate. A human stepping through without knowing those risks would be reckless. It's far safer and smarter to start with information. Imagine two stations connected by a newly constructed wormhole. At first, the engineers wouldn't be asking, "Can we walk through?" They'd be asking, "Can a signal survive?" They might set up synchronized atomic clocks on both sides and send time codes back and forth. If the clocks stay perfectly aligned, it means the wormhole isn't distorting time in unexpected ways. If there are delays or drift, that's a sign something deeper is happening to the flow of time between the two ends. Then they'd test the integrity of the data itself. Send a simple binary file, all zeros and ones, and check if it comes out exactly the same on the other side. If even a few bits are flipped, that could mean radiation, interference, or some unknown quantum effect is corrupting the signal. Only after countless successful transfers would they start trying more complex data. Compressed images, high-definition video, streams of sensor readings. And if it works, the implications are massive even before a single person ever steps through. A wormhole capable of carrying data instantly would make the concept of distance meaningless for communication. Messages to the far side of the solar system, which today take minutes or hours depending on where the planets are in their orbits, could arrive instantly. A spacecraft near Jupiter could talk to mission control in real time. A colony orbiting another star could have a live conversation with Earth. This changes not just exploration, but every aspect of coordination. Navigation systems could be updated without delay. Remote machinery could be operated with zero lag. Scientists could run experiments in distant environments and see results as if they were right there. Even emergency responses would be transformed. No more waiting for hours to know if a distress signal was received. Of course, there's a catch. Sending data is much easier than sending matter, but it's still not effortless. The wormhole would have to be stable enough to allow photons, particles of light, which carry the information, to pass through without being scattered or absorbed. That might require fine-tuning the wormhole's geometry, or shielding it from stray particles and fields. If the wormhole is microscopic in size, data transfer might be possible long before any physical object could pass through, simply because photons don't need much room. There's also the question of security. Instant communication is a powerful tool, but it's also a potential weapon. Whoever controls the wormhole controls the flow of information. And in a connected civilization, that's an enormous amount of power. Governments and organizations might race to create encrypted, secure channels through the wormhole, knowing that whoever listens in could access everything from private conversations to military strategy. Once data transfer is proven safe, the next step would likely be sending non-living objects, probes, containers, carefully chosen test payloads. These would be equipped with sensors to measure acceleration, temperature, radiation levels, and any other factors that could affect living beings. Engineers would look closely for anomalies. Did the object arrive at exactly the same temperature it left? Was its mass unchanged? Did its atomic structure remain stable? Even tiny deviations would be treated as red flags. Only after passing those tests would biological samples be considered. Maybe at first, it's just seeds or bacteria. Resilient, easily studied forms of life. They would be checked for mutations or biochemical changes after the journey. If nothing unusual appeared, the progression would continue. Small animals, then larger ones, always with long observation periods in between. The first human travelers would likely be volunteers trained for every imaginable emergency. By the time that moment came, we would already have been using the wormhole for years, not as a pathway for people, but as a pipeline for information. And that's not just a precaution, it's a practical advantage. Data can travel back and forth millions of times, creating value without risk, while the slow process of safety testing moves forward in the background. It's even possible that some wormholes would never be used for human travel at all. A stable, data-only wormhole would still be priceless. It could link observatories across the galaxy into a single network, giving humanity a telescope with a baseline as long as the wormhole's separation. It could create a distributed computing network that spans light years, with every node connected instantly. It could even become the backbone of a galactic internet, where the speed of light is no longer a barrier to connection. So when we imagine the first true wormhole, we should picture less of a grand first step into another world and more of a quiet moment. A row of scientists watching screens, holding their breath as a stream of numbers flows through a tunnel in space-time, unchanged. The first thing through won't be us. It will be the proof that the universe can be bridged and that the bridge holds. Chapter 8. When a wormhole becomes a time machine without trying. One of the strangest and most unsettling ideas about wormholes is that you don't have to design them as time machines. If you're not careful, they might turn into one on their own. And the reason isn't some mystical movie-style twist. It's a direct consequence of Einstein's theory of relativity. A theory we've tested and confirmed countless times here on Earth. Relativity tells us that time is not an absolute universal clock, ticking the same for everyone. It bends and stretches depending on how you move and where you are. If you're traveling very fast or you're sitting in a strong gravitational field, time for you will run more slowly, compared to someone far away in a weaker gravitational field. We've measured this in the real world. Satellites in orbit experience time slightly faster than we do on the surface of the Earth. And atomic clocks flown around the globe on airplanes show tiny but measurable shifts in their readings. Normally, these effects are too small to notice. Nanoseconds here, microseconds there. But in extreme conditions, the differences can become dramatic. Now imagine we've somehow managed to create a stable, traversable wormhole. It has two openings. Let's call them mouth A and mouth B. To start, we keep both mouths in similar conditions. They sit still relative to each other. No extreme gravitational fields. No high speeds. Time flows at the same rate for both ends. If you step into mouth A, you instantly emerge from mouth B. And for both you and the wormhole, no strange time effects happen. But here's where the trouble starts. Suppose we decide to move mouth B, not just a gentle drift, but at a significant fraction of the speed of light, and we keep it moving for a while before bringing it back near mouth A. Relativity says that because mouth B was moving so fast, time at B has run slower than at A. Maybe A has aged a year, while B has only aged a few months. When you connect 2 points in space through a wormhole, you're not just connecting their positions, you're connecting their points in time. So now the instant connection between A and B also links 2 moments that are out of sync, and that's where things get weird. If the time difference is big enough, you could step into mouth A and emerge from mouth B in what, from A's perspective, is the past. Or you could go the other way and arrive in the future. You've essentially built a time machine without meaning to, just by moving one end of the wormhole. This isn't some untested speculation. The mathematics of general relativity predicts it. In the 1980s, physicist Kip Thorne and his colleagues explored the equations for wormholes and showed that time shifts like this are a natural, unavoidable consequence. If you combine a wormhole with relativistic motion or gravitational effects, you don't have to add any extra time travel science fiction. The physics does it for you. The implications are staggering. If wormholes could be made stable and safe, then with the right movement or gravitational manipulation, they could allow travel into the past, at least to the point where the wormhole was created. And that opens the door to all the classic paradoxes. The grandfather paradox, the information loop, the what if I stop myself from creating this wormhole problem. Scientists and philosophers have debated these scenarios endlessly, and there's no definitive answer. Some believe that the laws of physics would simply forbid paradoxes by ensuring events stay consistent, no matter what you do, a concept called the Novikov self-consistency principle. Others think the universe could branch into alternate timelines to avoid contradictions, essentially creating parallel histories. But there's another possibility, one that acts like a built-in safety feature. Maybe wormholes collapse the moment they become time machines. Some calculations suggest that as soon as a wormhole allows a closed time loop, quantum effects inside it would build up to infinity in a fraction of a second, blasting it apart. If that's true, nature might have a way of protecting causality, not by forbidding time travel in theory, but by making it physically impossible in practice. Even if we avoid turning a wormhole into a full-fledged time machine, smaller time differences could still appear just from practical use. Maybe one mouth orbits closer to a massive planet, experiencing stronger gravity and slightly slower time. Maybe one is aboard a moving station, traveling at high speed for years. Over long periods, even tiny differences in time flow could accumulate. That means you could step through and find yourself hours, days, or months ahead, or behind, the place you left. This isn't just a curiosity, it would complicate everything about using a wormhole. Imagine sending urgent supplies to a colony, only for them to arrive before the request was sent, creating confusion about who asked for what. Or running a research project with two teams on opposite ends of a wormhole, one always working slightly in the other's past. Even in these small-scale cases, communication, planning, and cause and effect become tangled in ways we're not used to. And if someone decided to deliberately exploit those time offsets, a wormhole could become the ultimate strategic advantage or danger. The ability to send a message into the past by even a few minutes could have consequences far bigger than traveling light years across space. So the dream of wormholes isn't just about crossing space instantly. It's also about facing the reality that space and time are inseparable. The moment we build a bridge across one, we are unavoidably altering the other. And if we ever get to that point, one of the first and most important questions we'll need to answer is not where does this take us, but when does it take us? Chapter 9. A window across the universe. When most people hear the word wormhole, they think of stepping through it like a doorway and ending up somewhere else. A cosmic shortcut, a tunnel for travel. That's the image that dominates science fiction. Ships disappearing into a shimmering hole and reappearing light years away. But there's another way to think about wormholes, one that might be just as groundbreaking and maybe even safer. Instead of walking through, what if we simply used a wormhole to look? Picture a wormhole as a perfect optical link between 2 points in space. One mouth is here in our solar system, floating quietly in orbit around the moon. The other sits far away, perhaps near a star cluster at the edge of our galaxy, or even in another galaxy entirely. The connection between them would be instantaneous, so light from the far end wouldn't have to travel across space the slow way. It would just slip through the tunnel, arriving here in real time. That means the mouth of a wormhole could function like a telescope. Not just any telescope, but the ultimate telescope. Right now, every image we take of the cosmos comes with a built-in delay. When we look at the moon, we see it as it was about a second ago. The sun, about 8 minutes ago. And the most distant galaxies, we see them as they were billions of years ago. This is because light, no matter how fast it travels, still needs time to cross those enormous distances. A wormhole breaks that rule. If it's stable and open, you could see the other end instantly. You could watch events happening now, not events from deep in the past. We could observe alien planets as they rotate, track storms on gas giants light years away in real time, and witness the movement of stars in other galaxies without waiting centuries for light to arrive. We could even point it at regions normally hidden from us, like the dense interiors of nebula, where dust blocks ordinary starlight, and see straight through because the light wouldn't be coming through space at all, it would be coming through the tunnel. This would completely change astronomy. The field has always been about looking further back in time, piecing together history from the light that finally reaches us. But with a wormhole window, we could shift to studying the present-day universe directly. Imagine scientists being able to monitor the core of a distant galaxy every second, watch black holes feeding on matter without the years of delay, or instantly check on regions of space where gamma-ray bursts erupt. It wouldn't just be more convenient, it would open an entirely new kind of science, where we're no longer just historians of the cosmos, but reporters seeing it unfold. Now think about the search for life. With telescopes, we're limited to hints, small shifts in starlight as planets pass in front of their suns, faint chemical traces in atmospheres, maybe a glimmer of light that could mean cities. A wormhole could let us skip the guesswork. We could point it toward planets in the habitable zone and simply look. You'd see their landscapes, their oceans, even whether they have weather patterns or artificial lights at night. If there were intelligent life, you might see their cities, their technology, perhaps even their faces. Of course, there's a flip side. Looking works both ways. If the other end is near a civilization, they could look right back at us. Privacy, as we know it, doesn't exist on a cosmic scale. But a wormhole would make that reality much sharper. Imagine waking up to find that somewhere across the universe, someone is watching Earth in real time, seeing every ship in our oceans, every plane in our skies, every city light. Would we try to cover our end of the wormhole? Would they? Or would we treat it like a shared window between worlds, negotiating rules about what we show and what we hide? The more you think about it, the more complicated it gets. If a wormhole can send light instantly, it can also send messages instantly, and anything else you can fit through the opening. That means an innocent telescope could become a transport route in seconds, and that changes the stakes entirely. A live view into another world isn't just a curiosity, it's a potential diplomatic contact, a trade route, or a security risk. The decision to open such a window wouldn't just be scientific, it would be political, ethical, and possibly military. Then there's the matter of control. Who would operate such a wormhole? Would it be run by a single government? A coalition of countries? A scientific council open to all? History suggests that once such a device exists, everyone will want access, and disagreements over who gets to look where could be intense. If the far end of the wormhole is near a planet with resources or strategic value, the temptation to send more than just a camera through would be almost impossible to resist. And yet the opportunities are staggering. Imagine a wormhole linked to a star system where planets are forming. We could watch entire worlds come into being, not as a slow sequence of blurry images, but as a live feed. We could monitor asteroids in distant systems for signs of danger to Earth, track comets before they swing toward the inner solar system, or study cosmic phenomena like supernovae from just meters away in wormhole terms, without risking equipment or lives. It's worth remembering that even in this just-looking mode, the science is tricky. Wormholes bend space-time so strongly that light passing through could be distorted. The edges of the mouth might act like a lens, warping the image. If the wormhole's interior geometry isn't perfectly stable, the view could shimmer or blur, making fine measurements harder. There's also the issue of light contamination. If the other end is near a bright star, the glare could overwhelm any instruments unless the wormhole is shielded or angled carefully. Still, the idea of a cosmic window is hard to let go of. For the first time, we could see the universe not as a map of ancient snapshots, but but as a living, breathing reality unfolding right now. We could watch the swirling storms on Jupiter-like worlds light years away, see the changing light on alien moons, maybe even watch civilizations rise and fall in real time. But here's the most haunting what-if of all. What if we pointed the wormhole somewhere random, just to see what was there, and something stared back? Not just the light from another world, but a deliberate gaze meeting ours, across a tunnel that could be crossed at any moment. Would we shut it down, wave back, or step through? In that sense, a wormhole used for observation might be more powerful than one used for travel. Travel is risky and expensive. It demands commitment. But looking? That's easy. All you need to do is open your eyes, and once you've seen what's out there, you might never be able to look away. Chapter 10. The fragile nature of a cosmic shortcut. When we talk about wormholes, it's easy to imagine them as permanent structures. Neat, round tunnels linking two far-off points, waiting patiently for us to step through. But the reality, at least according to what physics tells us, is much less certain. Wormholes, if they exist, are fragile. Not just fragile in the sense that they might wobble or shake, but fragile in a way that the entire thing could collapse in an instant. This fragility comes from the very thing that makes wormholes possible: the bending of space-time. In general relativity, mass and energy shape the fabric of the universe, creating curves and folds. A wormhole is an extreme case, a place where the fabric isn't just curved but folded so sharply it connects two regions directly. That folding is inherently unstable. The moment you try to pass something through it, even light, the energy and stress introduced can disrupt the balance. Physicists have looked at the equations and found that without something special to hold them open, wormholes would snap shut faster than light could cross them. You could have a wormhole opening in front of you, and it would be gone before a single photon had a chance to make the trip. That's how unstable the geometry is. To keep it open, you'd need what's called exotic matter, a form of matter with negative energy density. And we've never seen this kind of matter in nature in quantities large enough to do the job. Now, negative energy sounds like science fiction magic, but in physics, it's a real concept. In certain quantum effects, like the Casimir effect, energy levels can dip below what's normally considered zero. In theory, if you had enough of this exotic matter, you could create a pressure that pushes space-time apart, counteracting the wormhole's tendency to collapse. But in practice, the amounts required are astronomical. Even a wormhole just a few meters wide might need more negative energy than all the positive energy in the sun. Let's imagine for a moment that somehow we solve the problem. We've built a stable wormhole, supported by fields of exotic matter, and it's just sitting there, linking Earth to some distant point in space. That doesn't mean it's indestructible. Wormholes would still be incredibly sensitive to disturbances. A change in the exotic matter field, maybe from a fluctuation in the quantum vacuum, could destabilize the throat. A sudden gravitational wave passing through could stretch or compress the tunnel, warping its shape or even tearing it apart. The risk gets higher when you start sending things through. Every object carries energy, not just in the form of mass but also heat, motion, and electromagnetic fields. All of that energy has to be accommodated by the wormhole's structure. If too much enters at once, it's like overloading a bridge. The stresses can exceed the material's limits, and the whole thing can fail. In this case, the material isn't steel or concrete, it's the geometry of space-time itself. And here's the truly unsettling part. If a wormhole collapses while you're inside it, the physics becomes unclear. You might be ejected at one end or the other, or the tunnel could pinch off in such a way that you're trapped in a region of space that no longer connects to our universe. Some solutions to Einstein's equations suggest that this pinched-off region could become its own little pocket universe, isolated and unreachable. From the outside, you'd simply vanish. Even if collapse doesn't happen instantly, instability could make travel dangerous in more subtle ways. If the wormhole's throat narrows while you're inside, tidal forces, the difference in gravitational pull from one end of your body to the other, could become extreme. Just as falling into a black hole could stretch you into a long, thin shape, spaghettification, an unstable wormhole could distort and tear apart matter as it passes through. Then there's the possibility of feedback loops. A wormhole is a connection between two places, but it's also a conduit for energy. If one end is near a strong source of radiation, a star, a quasar, even a hot planet, that radiation could pour through to the other side. If the wormhole reflects or refracts some of that energy back, you could get a runaway cycle, with energy bouncing back and forth until the structure is overwhelmed. In extreme cases, the wormhole could even become a cosmic weapon by accident, channeling deadly bursts of energy to places that never expected them. This fragility means that wormhole operation wouldn't just be about building them, it would be about maintaining them. Constant monitoring would be essential. You'd need instruments measuring the geometry in real time, sensors detecting even the faintest shifts in the exotic matter fields, and emergency systems ready to reinforce the structure at the first sign of trouble. It would be like running a nuclear reactor in the middle of a storm. Safe operation would depend on both flawless engineering and constant vigilance, and yet the rewards would tempt us to take the risk. Fragile or not, a functioning wormhole would be too valuable to ignore. We might start cautiously, sending only unmanned probes through, making sure the tunnel can handle the stress. Over time, as confidence grows, we might attempt cargo shipments, then human travel. But every step would carry the unspoken knowledge that the tunnel could fail at any time, and that failure might not give any warning. There's also the question of sabotage. If wormholes are fragile, they're vulnerable. A small, deliberate disruption, introducing the wrong kind of energy, altering the exotic matter field, could destabilize or destroy them. That makes them a potential target in any conflict. In a way, the very instability that makes wormholes hard to use might also make them politically dangerous. Control over their operation wouldn't just be about managing travel, it would be about securing one of the most delicate and powerful structures in existence. One could argue that fragility is both the curse and the saving grace of wormholes. On the one hand, it limits their use. You can't just throw open a wormhole to anywhere and expect it to stay that way indefinitely. On the other hand, it prevents them from being abused too easily. If a wormhole could be opened and left permanently stable without maintenance, the consequences, strategic, military, even ecological, could spiral out of control. Fragility forces caution. Still, fragility also forces us to think about backup plans. If a wormhole collapsed, would we have another ready to take its place? Could we reopen the same path quickly? Or would we have to start from scratch? Would we keep redundant wormholes to the same destination, just in case? These questions move wormholes out of the realm of pure physics and into the realm of infrastructure planning. The same kind of thinking we apply to power grids, shipping lanes, and communication networks. Perhaps the most humbling thought is that fragility might not be a flaw at all. In the grand design of the universe, maybe wormholes aren't meant to be highways for matter. Maybe they're meant to be fleeting alignments, rare and unstable, offering brief glimpses between distant places before vanishing. That would make them more like cosmic shooting stars, something to be observed, studied, and appreciated, but not relied upon. But humans have a habit of pushing limits. If we found even a hint of a natural wormhole, we'd study it obsessively, build models, test stabilizing methods, and try to hold it open longer than nature intended. Whether that's curiosity or recklessness depends on how the story ends. In the end, the fragility of wormholes is both a warning and an invitation. It tells us that nature doesn't hand out shortcuts easily, that if you want to bridge the vastness of space, you have to work for it, and you have to respect the risks. But it also whispers that, with enough understanding and enough care, even the most delicate structures can hold, at least for a little while, and in that little while, a whole universe could open before us. Chapter 11. Could wormholes change time too? When we think of wormholes, we usually picture them as shortcuts through space, like tunnels that connect two distant locations in the universe. But in physics, space and time are deeply linked. Einstein's theory of relativity tells us that the universe isn't just a stage where events happen. It's a four-dimensional fabric of space-time. If you bend space, you bend time along with it. That's why the idea of wormholes quickly leads to an even stranger possibility: time travel. The connection comes from how relativity works. Imagine you have a wormhole with two ends, one near Earth, the other far away, perhaps orbiting a distant star. If both ends just float in space without moving relative to each other, you could use it as a door between those two places. But if you start moving one end at high speed, something strange happens. Relativity says that for an object in motion, time runs more slowly compared to one at rest. This is called time dilation, and it's not just theory, it's been measured with fast-moving satellites and even airplanes carrying atomic clocks. So if one mouth of the wormhole is accelerated to near light speed and then brought back, it will have experienced less time than the other mouth. The two ends will still be connected through the tunnel. But now there's a mismatch. Step through from one side, and you could emerge in the other side's past or future. It's not magic, it's geometry. The wormhole's interior doesn't care about how time passes outside it. It simply links 2 points in space-time as they exist right now at their ends. That means a wormhole could in principle be turned into a time machine. You could travel years into the future by going through one way, or years into the past by going the other way. The details depend on how you move the wormhole ends, and how long you wait before stepping through. In fact, you wouldn't even need to travel at near light speed. You could also put one mouth near something massive, like a black hole, where gravity slows time in much the same way as speed does. The result would be similar. The clocks on the two ends would fall out of sync. Of course, the moment you bring time travel into the picture, the questions get messy. What happens if you go back and change something? Could you meet yourself in the past? Physics doesn't give easy answers here. Some interpretations of relativity suggest that space-time might self-consist, meaning that events would adjust in a way that prevents paradoxes. In this view, if you went back through a wormhole to the past, you couldn't change something in a way that stops you from going back in the first place. Your actions would already be part of history. But other theories, especially in quantum mechanics, leave room for branching timelines. If a wormhole sends you to the past and you make a change, the universe might split into two versions, one where you made the change and one where you didn't. In that case, wormholes wouldn't rewrite your history, they'd just move you into a different branch of reality. That's a big what if, but it's one physicists take seriously in certain models. Then there's the question of stability. Turning a wormhole into a time machine isn't as simple as moving one end around. The moment you make a wormhole that allows travel to the past, you create what physicists call closed time-like curves, paths through space-time that loop back on themselves. In theory, these loops could amplify quantum fluctuations to the point of tearing the wormhole apart. It's as if nature itself tries to prevent time machines from existing by making them collapse the instant they become possible. This idea is called the chronology protection conjecture, famously suggested by Stephen Hawking. But what if chronology protection isn't absolute? Then the problems aren't just physical, they're social, political, even moral. Imagine having the ability to send information to the past. Even if you couldn't send a person, you could send a warning, or a stock tip, or a secret. Wars could be fought not with armies, but with well-timed messages that alter events before they happen. Governments and corporations would compete to control these channels. And if wormholes were fragile, as we've already seen, the temptation to sabotage them would be enormous. We'd also have to think carefully about access. Would anyone be allowed to use a wormhole that could change time? Or would it be locked away in the most secure facility on Earth, guarded like the most dangerous weapon ever built? Even with strict control, the risk of misuse would be constant. After all, history isn't just science, it's identity. If you can rewrite it, you can change who people are, what cultures become, and what futures are even possible. It's worth asking if we would even recognize the changes. If wormhole time travel altered the past in a way that rewrote the present, would we have any memory of the old timeline? Some theories suggest we wouldn't. The change would ripple instantly through everything, including our own minds. From our point of view, the new version of events would have always been true. Others suggest that subtle traces might remain, inconsistencies, déjà vu, or records that somehow don't match. It's unsettling to think about. But maybe there's a middle ground. Perhaps wormholes wouldn't allow full freedom to move around in time. They might be limited by their own creation date, meaning you couldn't go back to a time before the wormhole existed. That would close off the possibility of visiting ancient history or meeting long-dead figures, but it would still let you loop within a certain window. Even a few years of reach into the past could be enough to revolutionize science, medicine, and space exploration. There's also the possibility that wormhole time travel would only work in one direction. You could travel to the future but not return. In that case, wormholes would act like one-way tickets, letting us skip ahead in time but not undo what's been done. That might make them less dangerous but still incredibly tempting. A way to leapfrog centuries of waiting and see what humanity becomes. The physics doesn't forbid these ideas outright. It just makes them extremely difficult to achieve. The energy requirements, the need for exotic matter, the precision needed to manipulate space-time, all of these are monumental challenges. But history is full of technologies that once seemed impossible until the right discovery made them inevitable. The question is whether wormhole time travel would be one of those breakthroughs we embrace, or one we decide to avoid. And maybe avoidance is the wisest choice. The power to move through time could magnify every human strength and weakness. It could heal or harm on scales we can barely imagine. Just as nuclear technology gave us both power plants and weapons, wormholes could give us both unprecedented exploration and unprecedented manipulation. The line between the two might be razor thin. In the end, wormholes remind us that space and time aren't fixed backdrops. They are flexible, dynamic, and deeply intertwined. Bending one bends the other. And the deeper we explore those bends, the closer we come to the limits of what our universe allows. Whether time travel through wormholes is a door we'll ever open is still unknown. But even the thought of it forces us to confront a bigger question. Not just can we do it, but should we? Chapter 12. Who controls the gate? The politics of wormholes. When people talk about wormholes, they often focus on the science, the physics of bending space-time, the strange matter needed to hold a tunnel open, or the engineering that could keep it stable. But if wormholes ever became real, the story wouldn't end with scientists and engineers. It would quickly spill over into politics, law, economics, and human behavior. A wormhole isn't just a piece of technology. It's a connection between places that could change everything from travel to trade to security. And that means someone, somewhere, would have to decide who gets to use it. The moment a wormhole exists, control becomes the central issue. In today's world, even things as basic as bridges, shipping routes, or internet cables are carefully regulated. Wormholes would be far more significant. They'd be instantaneous links between distant parts of the Earth, or even between planets and stars. Whoever controlled one could decide who passes through, what goods move, and what information flows. That kind of power wouldn't just make someone influential. It could make them the most important decision-maker in history. Think about the scale of this. If there were only one or two functioning wormholes in existence, they would be the rarest and most valuable infrastructure ever created. They would probably be treated like strategic assets, guarded by military forces, surrounded by laws and treaties, and monitored by intelligence agencies. Access might be restricted to governments, or perhaps a coalition of countries. But history suggests that even if the control started in the hands of many, it could end up in the hands of a few. The distribution of wormholes could shape the balance of global power. Imagine if the first operational wormhole was built in one country. Even if they promised to share it, the reality is that control over its physical location would give them enormous leverage. They could set fees, priority rules, or political conditions for its use. Other nations might try to build their own wormholes just to avoid dependence, triggering a technological race. And what about private companies? In today's space industry, corporations already operate rockets, satellites, and deep space missions. It's not hard to picture a future where a wealthy corporation develops the first stable wormhole. They could charge enormous sums for access, creating a monopoly over instant space travel. In some ways, this could mirror how private companies control parts of the internet or dominate certain transportation industries. The difference is that wormholes wouldn't just move data or goods. They could move people anywhere in the galaxy. This leads to another question. How do you keep a wormhole safe? If anyone could step through, they could bypass borders entirely. Customs checks, immigration controls, even military defenses, all of these could be undermined by an unregulated wormhole. That's why control wouldn't just be about ownership. It would also be about security. You'd need systems to monitor who enters and exits, scanners to detect dangerous materials, and agreements to handle disputes when something illegal passes through. But there's a deeper layer to this. Wormholes could also move not just people and goods, but ideas instantly. Imagine a repressive government trying to control the flow of information in and out of its borders. A wormhole could make censorship almost impossible. At the same time, it could also make propaganda and misinformation spread faster. Control over the gate would mean control over the world's fastest, most powerful communication channel. This is where international politics would come in. The world has dealt with game-changing technologies before: nuclear weapons, the internet, space travel, and each time, global treaties and agreements have tried to manage their risks. A wormhole would likely be covered by its own version of these agreements. Maybe the United Nations or a new international body would oversee them. Perhaps the wormhole would be placed in a neutral zone, like Antarctica or space, where no single country has sovereignty. Still, treaties are only as strong as the trust behind them. If one nation suspected another of using a wormhole for secret military movements, espionage, or smuggling, tensions could escalate fast. Wormholes could even become targets in conflicts. Damaging one could cut off entire regions from instant travel or communication. Defending them might require constant military presence, not just on one end but on both, which becomes even more complex if the two ends are on different worlds. Then there's the question of fairness. If wormholes are scarce, who gets priority access? Would they be reserved for scientific research, for humanitarian missions? Or would the first slots go to the highest bidder? Even if governments promise to use wormholes for the benefit of all humanity, the temptation to use them for national or corporate advantage would be enormous. Trade routes that once took weeks or months could be replaced overnight, disrupting economies and leaving entire industries obsolete. And what about the ethical side? If a wormhole connects Earth to another planet with its own ecosystems, who decides what can be sent through? Could someone start transporting resources from another world without permission? Could invasive species accidentally or deliberately be moved from one planet to another, with catastrophic consequences? Here, control wouldn't just be about politics or money. It would be about protecting entire worlds from harm. One solution could be a layered system of governance. Local authorities could manage the immediate area around each wormhole mouth, while a global or interplanetary organization sets the rules for what can pass through. This might be similar to how air travel works today. Airports are run locally, but international aviation is governed by shared agreements. The difference is that wormholes could involve far more stakeholders, from multiple planets and civilizations if they exist. We also have to consider the human factor. History shows that no matter how strict the rules, someone will try to bypass them. Smugglers, hackers, and black market traders could see wormholes as the ultimate opportunity. Even with advanced monitoring systems, it would be impossible to check everything moving through a wormhole without slowing it down. And part of the appeal of a wormhole is its speed. That means enforcement would always be a challenge. Then there's the possibility that wormholes could be private and hidden. If building one is possible on a small enough scale, someone could create a secret connection known only to them. That would take the idea of unofficial borders to a whole new level. Governments might pour resources into trying to detect and shut down unauthorized wormholes, just as they do today, with certain types of encrypted communications or underground networks. It's interesting that in all these scenarios, the core issue isn't whether wormholes work. It's how people use them. Technology often moves faster than our ability to regulate it, and wormholes would be no different. The biggest risks might not come from engineering failures or exotic matter running out, but from human ambition, greed, and fear. If wormholes ever become real, the debate over who controls them might last longer than it takes to build them. It might even shape the entire course of human civilization in space. Will they be public highways for everyone, or gated corridors for the few? Will they unite distant worlds, or divide them even more sharply? The answers would depend not on physics, but on politics, and on whether humanity can resist turning the most remarkable tool for exploration into just another weapon in the struggle for power. Chapter 13. Wormholes as cosmic lifeboats. When we imagine wormholes, we often picture them as tools for discovery, a way to reach far-off worlds, to satisfy our curiosity about the universe. But there's another side to them, one that makes them far more than a scientific luxury. In a dangerous universe, they could be the ultimate safety device, a cosmic lifeboat. The threats to a planet like ours are many. Some are slow, creeping changes, a warming star, a shifting orbit, or gradual atmospheric decay. Others are sudden and violent. Asteroid impacts, supervolcanoes, gamma-ray bursts, or even the chain reaction of a nuclear war. In our current reality, the only escape from such events would be to launch ships, a process that takes years of preparation and is limited to tiny numbers of people. A wormhole changes the equation entirely. It offers a doorway. Step through, and you are somewhere else, instantly, completely, without the limitations of conventional travel. Picture an evacuation on a planetary scale. A wormhole could open in a central location, a spaceport, a city square, or an orbital station, and remain active as millions pass through. Families, equipment, cultural records, even parts of the ecosystem could be relocated in days or weeks rather than centuries. If one end of the wormhole led to a safe, prepared destination, a habitable planet, a large station, or even a purpose-built artificial world, survival would be measured in logistics, not in the speed of ships. But this raises questions. Where does the lifeboat lead? In fiction, we sometimes imagine perfect worlds waiting for us on the other side. But in reality, finding or creating such a place is its own massive challenge. If wormholes could be made stable and directed, we might link them to planets already known to be safe. If we had no such options, they might open to uninhabited worlds where survival would still depend on rapid building, farming, and adaptation. The wormhole would give us the chance, but not the guarantee of survival. Then there's the issue of preparation. Wormholes are not something you can set up at a moment's notice, at least not with our current understanding of physics. Even if we could create them, the process would likely be energy-intensive and technically complex. That means the lifeboat would have to be in place before disaster strikes. The what-if scenario becomes a planning problem. Governments or organizations might maintain permanent wormhole links to backup worlds, much like we now keep emergency shelters or disaster recovery sites for data. Yet, wormholes as lifeboats bring risks of their own. Connecting two places means whatever is in one environment can pass into the other. People, animals, microbes, pollutants. In the chaos of an evacuation, those risks multiply. The wrong species could be introduced into a fragile ecosystem. Pathogens from one world could wreak havoc on another. Quarantine and screening would have to be part of any large-scale movement through a wormhole, even in an emergency. And there's the political side. Who gets to use the lifeboat? If the danger comes with limited warning, choices have to be made. Who passes through first? Who is left behind? And who decides? In a perfect world, the wormhole would be wide enough, stable enough, and accessible enough for everyone. But physics may not allow that. There may be bottlenecks. The wormhole's aperture might be small, its energy demands limiting how long it can stay open, or its location unreachable for large populations. Those limitations mean ethics and governance would matter as much as engineering. One possibility is to keep smaller, personal-scale wormholes, portable units that can connect to a larger evacuation hub. Imagine a network of small, stable links feeding into a main wormhole that leads to safety. People wouldn't need to travel far. They'd step into the nearest unit and emerge at a centralized departure point. It's a distributed version of the lifeboat idea, one that reduces crowding and increases reach. We also have to consider the problem of the other end. If millions arrive suddenly in a new place, how does that place cope? Overcrowding could turn survival into a different kind of crisis. Shortages of food, water, housing, and medicine. A wormhole evacuation might solve the problem of getting away from danger, but leave the harder challenge of building a stable new society from scratch. There's also the risk of chasing danger rather than escaping it. In a vast universe, not all threats are stationary. If the safe world on the other end is in a galaxy where a supernova chain is unfolding, or if its star is unstable, the lifeboat could lead from one crisis to another. Ideally, the backup world would be monitored constantly, with data flowing both ways, so we'd know if it remains safe. From a purely physical perspective, the engineering requirements are staggering. Wormholes would need to be stable under immense environmental stresses, large enough to move people and supplies, and precisely targeted to a location that can sustain life. They would also need mechanisms to remain open for extended periods, perhaps days or weeks without collapse. The energy demands alone could rival those of entire civilizations. If it's possible at all, it would require an infrastructure that spans decades of planning and planetary-scale cooperation. But the promise is too big to ignore. For every civilization in the universe, if there are others out there, survival may depend not on ships, but on links. In that light, wormholes stop being exotic tools for explorers and become something far more practical: insurance against extinction, a cosmic fire escape, a backup copy of life kept somewhere far from where it began. If the universe ever hands us the ability to build such a thing, we may find that its first use is not for curiosity or adventure, but for survival. And if we're wise, we'll prepare for that long before we think we'll need it. Because in the history of life, the biggest disasters are often the ones no one saw coming, and a lifeboat you haven't built is no lifeboat at all. Chapter 14. Building the bridge. Engineering a stable wormhole. If wormholes are ever going to move from the pages of theory into the realm of everyday tools, the biggest challenge isn't convincing people they're worth building, it's figuring out how to make them in the first place. The idea of a shortcut through space sounds simple enough when drawn on paper. 2 points, one curve connecting them, and a tunnel that bypasses everything in between. But the engineering reality is far less forgiving. The bridge between worlds has to be more than just a concept. It has to hold. The first problem is stability. Wormholes in the equations of general relativity don't naturally stay open. Left to themselves, they collapse almost instantly, pinching shut before anything. Even light can get through. To keep one open, you'd need something to hold it apart, to counter the immense gravitational forces that want to close the throat. This is where the idea of exotic matter comes in. A form of matter with negative energy density that would create repulsive gravitational effects. In other words, the opposite of normal mass. The problem is, we've never found enough of it to do anything useful, let alone enough to keep a planetary-sized tunnel in space propped open. Even if exotic matter exists and could be used, the engineering would be staggering. We'd need to arrange it in a precise geometry, creating a balanced structure that can withstand pressure from both ends of the wormhole. The tiniest imbalance could send shockwaves through the tunnel, distorting it or snapping it shut. That means any wormhole system would require constant monitoring, sensors spread throughout its structure, feeding data to control systems capable of making corrections in real time. Then there's the issue of size. A wormhole, only a few centimeters across, is useless for moving people, equipment, or vehicles. Expanding it to a size large enough to drive a ship through, or even an entire city block, multiplies the stresses and the energy demands. Scaling up is not just a matter of more power, but also maintaining the same structural integrity. Imagine trying to inflate a fragile balloon until it's the size of a football stadium, all while keeping its shape perfectly uniform. And size isn't the only spatial concern. Where does the other end go? In theory, a wormhole could connect any 2 points in space, but hitting the right location with precision is a monumental task. Space isn't static. Planets orbit, stars move, galaxies drift. If the exit point of a wormhole isn't constantly recalculated and adjusted, you could open the door expecting to step onto a planetary surface and instead find yourself floating in deep space, thousands of kilometers away. The navigation systems would have to be incredibly accurate, factoring in every relevant gravitational influence between the 2 points. Once you've placed your wormhole, you have to anchor it. Without some sort of anchoring mechanism, gravitational, magnetic, or structural, the ends could drift, twisting the tunnel, or creating unpredictable fluctuations. An unanchored wormhole is like a hose flailing under pressure, but with the added danger that one end could snap into a region of space you never intended to reach. Then there's safety. Wormholes could become unstable if too much mass moves through them too quickly. If the flow of matter isn't controlled, the stresses might ripple down the tunnel, distorting it or tearing it apart. That means there would need to be limits on how fast ships can pass, on the total weight transferred in a given time, and on what kind of materials are allowed through. In the worst-case scenario, an overloaded wormhole could collapse while something is inside it. What happens to that object is unknown, and probably not something anyone would want to find out. Energy remains the elephant in the room. Even a small wormhole might require more energy to sustain than a planet produces in a year. That means any working system would need an energy infrastructure, orders of magnitude beyond what we currently have, perhaps tapping directly into the output of stars via vast solar collectors, or using controlled black holes as power plants. If wormholes become possible, the first real engineering breakthrough might not be the tunnel itself, but the power system that can keep it alive. And then comes redundancy. A single wormhole link is vulnerable. If it fails, the connection is lost instantly. In a transportation or evacuation system, that's not acceptable. Engineers would need to build networks, multiple routes linking the same destinations, backup tunnels ready to activate if one collapses, and a web of smaller wormholes connecting key points in space. The challenge here isn't just technical, but logistical. Keeping dozens or hundreds of high-energy, precision-maintained structures operating simultaneously would require an organization on a scale humanity has never attempted before. Finally, there's maintenance. Space isn't empty. It's filled with radiation, particles, and gravitational fluctuations. Over time, those effects could wear on the wormhole's structure, creating distortions or instabilities. Maintenance crews, whether human, robotic, or both, would need to travel inside or alongside the wormhole to make repairs. That presents its own danger. You'd be working inside a structure that exists because of delicate balance, and any wrong move could collapse it around you. All of these challenges add up to one conclusion. If wormholes ever become real, building one won't be like flipping a switch. It will be the most complex engineering project in history, requiring the combined knowledge, resources, and cooperation of entire civilizations. The bridge between 2 points in space will be as much a monument to collaboration as it is to physics. In the end, the science might give us the possibility, but the engineering will decide whether we can actually step through. And if we succeed, the first person to walk across that bridge will do so knowing that behind the simple act of stepping forward lies a story of decades, maybe centuries, of problem-solving, trial and error, and the patient work of turning an impossible curve in space-time into something you can walk through without a second thought. Chapter 15. The economics of a shortcut through the universe. The moment you give any civilization the ability to move instantly between 2 distant points in space, the rules of economics begin to shift. Wormholes wouldn't just change travel times. They'd rewrite supply chains, resource distribution, and even the meaning of distance itself. In our current world, the cost of moving goods is tied to fuel, time, and risk. Long shipping routes add expense. Delays can ruin perishable products. Strategic choke points, like straits or canals, give certain locations immense power over global trade. Now imagine replacing a 6-month journey with a 6-second walk. Minerals from an asteroid belt could arrive on Earth before the mining dust settles. Medical supplies from a colony light years away could reach a distant planet's hospital the same day they're manufactured. The speed alone would cut the cost of transport dramatically, but the real economic shock would come from how it changes access to resources. Scarcity is one of the engines of value. Gold is valuable partly because it's rare and hard to get. But if a wormhole opens directly between Earth and a gold-rich exoplanet, supply could surge overnight, dropping prices and reshaping entire industries. The same would happen with rare elements, food crops, or even fresh water. Markets would adjust, but the adjustment wouldn't be painless. Some regions might lose their economic advantage entirely, while others would suddenly find themselves in the middle of a trade explosion. Energy economics could shift too. Planets or moons rich in solar exposure or geothermal activity could export massive amounts of power through the wormhole network, transmitted as fuel cells or even as beamed energy. This could end energy scarcity in some places, but also create dependencies, where entire worlds rely on a single source. In economics, dependence can be as dangerous as shortage. Transportation industries would face upheaval. Ships, freighters and cargo haulers designed for long-haul space travel might become obsolete almost overnight. At the same time, new industries would emerge around the wormhole gateways, stations, security systems, traffic management, and maintenance. Gateway cities could spring up at both ends, acting as hubs for commerce, trade negotiations, and storage. These could become the economic capitals of the galaxy, much like port cities on Earth flourished during the age of ocean trade. Trade routes themselves would compress into narrow corridors, not across open space, but between fixed wormhole points. Whoever controls those points controls the flow of goods. That means wormhole ownership could become the most valuable asset in the galaxy. Governments, corporations, or coalitions might guard their wormhole stations as fiercely as ancient cities guarded their walls. Tolls could be charged for passage, trade agreements negotiated for preferential access, and entire economies might be built around regulating and taxing what goes through. The speed and reliability of wormhole travel could also encourage new forms of commerce. Just-in-time manufacturing could become the galactic standard, with parts shipped instantly from dozens of worlds to be assembled somewhere else. Perishable goods could be traded across unimaginable distances. Fresh fruit from a tropical exoplanet in a cafe on Mars. Seafood caught that morning on an ocean world, served for dinner on a station orbiting Alpha Centauri. But wormhole economics wouldn't be purely positive. Instant trade could destabilize local markets. Small planetary economies could be flooded with cheap imports, crushing local producers who can't compete. Wealth could concentrate even more heavily in the hands of those who control or have early access to wormhole routes. Economic inequality between connected and unconnected worlds could grow rapidly, with wormhole-linked planets thriving while others stagnate. There's also the question of currency. Right now, money systems are tied to geography, politics, and trust, with wormholes connecting worlds instantly. A universal currency might become more practical, but also more volatile. Exchange rates could swing wildly if a major resource discovery suddenly shifts the economic balance. A unified currency might stabilize trade, but deciding who controls it and how it's managed could be one of the most politically charged debates in history. Insurance, too, would take on a new form. Moving goods through a wormhole might be nearly instantaneous, but the risks could be very different from traditional transport. Wormhole collapses, energy fluctuations, or political blockades could cut off a vital route without warning. Entire shipments could be lost in an instant if a tunnel destabilizes mid-transfer. Insurers would have to develop entirely new models for calculating premiums and payouts. The biggest long-term economic change might come from labor. If people can move instantly between worlds, job markets are no longer local. A skilled engineer on one planet could take a contract halfway across the galaxy without relocating permanently. Cultural exchange would accelerate. Remote work could become galactic work, with teams spread across multiple star systems, meeting in person as easily as we now make a video call. Yet, with all these transformations, there's one thing history tells us clearly. Technology doesn't erase old inequalities, it shifts them. In the same way that railways, ships, and the internet created both opportunity and exploitation, wormholes would give some players a massive advantage over others. How fair or unfair that system becomes would depend less on the physics of wormholes and more on the policies, agreements, and ethics we build around them. In short, wormholes wouldn't just be an engineering feat, they'd be an economic earthquake. The physics might open the door, but what happens after we step through would depend on the decisions we make as traders, lawmakers, and neighbors in a connected galaxy. The bridge between 2 points in space would also be the bridge between 2 economies, and what travels across it will shape more than just markets. It will shape the future of civilization itself. Chapter 16: The Reality Check. Do wormholes truly exist? We've traveled far in our imagination. We've pictured wormholes as shortcuts for explorers, as lifeboats for civilizations, as engines for economies and politics. But now we need to pause and ask, how much of this belongs to the real universe, and how much is only speculation? The idea of a wormhole is not science fiction at its root. It is science. In 1935, Albert Einstein and Nathan Rosen described what came to be called the Einstein-Rosen bridge. In the mathematics of general relativity, it was possible to imagine tunnels that connect 2 regions of space-time. They weren't stable, they weren't practical, but the equations didn't forbid them outright. From that moment, physicists had to take wormholes seriously, not as proven things, but as possibilities. The problem begins with stability. According to Einstein's equations, a wormhole pinches shut almost instantly. To hold it open, something unusual would be required: negative energy, or what physicists sometimes call exotic matter. Negative energy isn't just a poetic phrase. In quantum physics, strange fluctuations in empty space, what we call the vacuum, can produce effects that look like negative pressure. This isn't the kind of matter we interact with every day, and we don't yet know whether it exists in a usable form or in enough quantity to stabilize a wormhole. This brings us to the Casimir effect, a real experiment that gives a tiny glimpse into this realm. When 2 metal plates are placed extremely close together in a vacuum, quantum fluctuations are restricted between them, creating a measurable force that pushes the plates together. Some interpret this as evidence that negative energy states can exist in limited conditions. But scaling something like that up from micrometers to meters, let alone kilometers, is a leap that science cannot yet make. Then there's the issue of size. If wormholes exist at all, some physicists suspect they might be hiding at the quantum scale. Smaller than atoms, opening and closing constantly in what's called quantum foam. These would be useless for travel, unless there were a way to enlarge and stabilize them. Others suggest that cosmic-scale wormholes might have formed in the early universe during its violent expansion. If any survived, they could still be out there, but detecting one would be harder than finding a needle not just in a haystack, but in the cosmic haystack of space itself. There are also the paradoxes of time. Some solutions in general relativity suggest that wormholes could connect not only 2 points in space, but also 2 different times. That opens the door to time travel, and with it, the famous paradoxes. What happens if you change the past, or if an event loops into itself? Most physicists lean toward the view that nature forbids these contradictions, possibly through mechanisms we don't yet understand. In fact, some argue that quantum effects would destroy a wormhole the moment it could be used for time travel. It might simply not be allowed. Practical engineering challenges loom even larger. Even if a wormhole could be created and stabilized, the amount of energy required could be astronomical. Some estimates suggest it might take the energy output of an entire star just to open one tunnel wide enough to send a spacecraft through. For comparison, humanity's current total energy use in a year is tiny next to the energy released by the sun in a single second. The scale of power needed is beyond our reach for now. Still, physics doesn't close the door completely. The equations allow the possibility, and that sliver of possibility keeps the discussion alive. Wormholes become a kind of thought experiment that helps physicists test the edges of theory. By asking, what if wormholes exist? We explore questions about energy, quantum mechanics, and the very fabric of space-time. Even if we never build one, the effort deepens our understanding of the universe. It's worth remembering that many ideas once thought impossible have eventually become part of ordinary life. Flight, electricity, nuclear power, even black holes, all began as speculation or strange mathematical curiosities. The difference is that those ideas eventually found experimental evidence and engineering pathways. Wormholes, so far, have not. So where does that leave us? With imagination, grounded by caution, wormholes may remain forever in the realm of what if, or they may be discovered one day, hiding in the data of gravitational waves, or the flicker of light from a distant galaxy, or in the mathematics of a future theory that unites quantum mechanics and relativity. And if they never turn out to be real, the thought of them still matters. Because by imagining wormholes, we imagine connection. We imagine moving past limits, bridging distance, surviving challenges, and sharing across impossible divides. The physics of wormholes may not be within our reach, but the mindset of wormholes, the willingness to ask what if, is something we can use every day, even here on Earth. That's the true power of the idea. Whether or not wormholes exist, they teach us how to think bigger than our immediate horizon. They remind us that even the most impossible-sounding doorways might, one day, turn out to be real. Until then, we wait, we calculate, we explore, and we wonder.